We are on page 11 of our acid-base notepad, and today's lesson will be discussing the relationship between Ka and Kb, the acid dissociation constant and the base dissociation constant. Pretty much at the top of page 11 where we see section 16.8. If we consider a conjugate acid-base pair, and for an example we'll begin with two familiar molecules, the ammonia molecule and its conjugate, the ammonium polyatomic ion. Each of these species, of course, could react with water. And let's just take a quick look at what that would look like into our notepad. And let me just extend the page a little bit and we'll write these things together. So where it's asking us to write the reactions for the two species in water, let's start with the NH4 plus, the ammonium polyatomic ion, and let's place that into water and see what would happen. Of course, here we would label the ammonium as an acid, and water would be acting as a base. Acids we know are proton donors. This is a positive one. Let me make that clearer. Proton donors, so the ammonium donates its proton to the water. Ammonia, the conjugate base of ammonium, forms, and the hydronium ion, H3O+, the conjugate acid of water. So remember, we are just doing some Bronsted-Lowry theory where we're hooking together conjugate pairs. Take, for example, the second molecule, ammonia, NH3. If this is indeed placed into water, we set up some equilibrium, and the conjugates come back at us. If ammonia is acting as a base, water here acting as the acid. Remember that term, amphoteric. Water in one condition is acting as a base, and in the second condition is acting as an acid. The conjugate pairs, ammonium, the conjugate acid of ammonia, and of course hydroxide, the base ion, the conjugate base of water. So a little Bronsted-Lowry review to set up the relationship between Kas and Kbs. We would see in the first reaction ammonium is acting as an acid. It would therefore have what we call a Ka expression. It's producing the acid ion, hydronium. Here in the second equation, ammonia is acting as a base. Therefore, we know it would have a Kb expression, B for base. It's forming the base ion, hydroxide. Let's express the Ka for the top equation. No numbers, just the expression, where it's the products over the reactants. The molecules here of NH3, the acid ion, hydronium, H3O+. Remember how the liquid water drops out of an equilibrium expression, so the only thing remaining on the bottom is NH4 plus 1, the ammonium polyatomic ion. Let's express the Kb for the second equation. It's a Kb because we produce the base ion. The concentration of the conjugate acid ammonium times the concentration of the base ion, hydroxide, all set over ammonia, NH3. The Ka expression for our first equation, and here's the Kb expression for the second equations. We're being asked to add the equations together. Well, we understand when we add the equations, and just to kind of clarify, if we look at here, everything on the left and everything on the right put into one big equation. Let's model that. Let me see if I can't keep the equations on the screen as well. Let's add them together, and let me put that in a different color. So everything on the left side, we have NH4 plus, we have some water, and we have ammonia. Now I'm just going to leave the water out because I know that it will end up dropping out of our expression anyway. You can see that it does not appear in the expressions. So ammonium plus ammonia, and that's what I'll do for my equilibrium. We have NH3 on the right-hand side. We have hydronium, H3O+. We have ammonium, NH4+. And we have a hydroxide, OH-. See anything that can simplify? Well, both the conjugate pairs, don't they? Ammonium appears on both sides. It can be simplified. And of course, the ammonia can be simplified. So really what's left, and if we just make the water appear, remember that there's two water molecules here, not part of the expression, so I'll just leave them in red knowing that they don't appear in the expression. However, two water molecules bombard and they dissociate. We called this the ion product constant for water. When two water molecules dissociate, H3O plus and OH negative come out. This was the ion product constant for water. It had its own little K and it was subscripted with W. Kw, the equilibrium dissociation for water. Well, what have we just shown? We started with two conjugate pairs, ammonium and ammonia. We showed in the Bronsted-Lowry theory their dissociation and how ammonium with its Ka and ammonium with its Kb, ammonia with its Kb, when added together, came right back and gave us Kw. In other words, we have a relationship. If this is the expression when we added Ka, remember when we add equations, we multiply the K constants, we came up with Kw. There indeed is our relationship between Ka and Kb. I've lost my spot here, hang on. There's where I wanted to be. So here's our relationship. We said that the value of Ka times the value of Kb indeed is the constant we called the ion product constant for water, Kw. It's equal to the acid ion, H+. Remember that we could also see that as H3O+ for hydronium, times hydroxide, giving us the constant 1 times 10 to the negative 14. Another way of writing that, pKa plus pKb is equal to pKw, which of course is 14. Looks very familiar, doesn't it? Remember this one? pH plus pOH is always 14. pKa plus pKb is always 14. And that's simply because Kw is the product always produced when we multiply the Ka expression times the Kb expression. So this relationship will come in very handy when we want to convert a Ka into a Kb or vice versa. Let's take a peek at this example. With our Appendix D, we are being asked to calculate a Kb for the fluoride ion. And let's just call that example 1, and then we'll look at example 2, the Ka for ammonium. The fluoride ion in example 1, F negative fluoride, when it's placed into water, we set up an equilibrium where the conjugate acid of fluoride forms and the conjugate base of water forms. We hook together the conjugates using the Bronsted-Lowry theory. Fluoride is acting as a base. It produced its conjugate acid. Water here is acting as an acid, producing its conjugate base hydroxide. We can very clearly see that this would represent a Kb expression because we're producing the base ion. Kb, no numbers, but just the expression, would take the products over reactants. HF times the concentration of OH negative all over the concentration of fluoride. We're being asked to find the value, calculate the value of Kb using our Appendix D. And that was the test-taking tool page I had handed to you on Friday. If you look over, there is a very tiny table for Kb's on the top of page 1127. So here I am in Appendix D, and no matter how I can stare at the Kb, there aren't very many. I do not see the fluoride ion. However, look at the Ka, which is a much larger table, and I want you to find the conjugate acid of our base. Remember here, if fluoride is our base, its conjugate acid is HF. That I can find using Appendix D. Skimming through for hydrofluoric acid, HF, looks like 6.8 times 10 to the negative fourth. Yep, I found that right. 6.8 times 10 to the negative fourth. There's its Ka, but we need to transfer that into a Kb. So remember our relationship, Kw is equal to Ka times Kb. And here's what we know. Kw is a constant. It means it never changes. Its value is 1 times 10 to the negative 14th. No units, it's a K constant. Kw is one we just looked up, 6.8 times 10 to the negative fourth. Let's pull out Kb. The Kb will be for the expression, what we just wrote earlier, of fluoride, the F negative ion, acting as a base. So you can clearly see the pattern of algebra. Kw divided by Ka will pull out our Kb. And hit that with me just to be sure we get a common answer. So 1e negative 14 divided by 6.8 e negative 4. And my calculator is saying for Kb, 1.47 times 10 to the negative 11th. So back to what giving this meaning here, this Kb has a constant. We just solved for it. The Kb for this expression, 1.47 times 10 to the negative 11th. The second example, the Ka for ammonium ion. So example number 2. Ammonium is NH4 with a +1 charge. When it's placed into water, it sets up an equilibrium with its conjugate base, ammonia, producing the hydronium acid ion. So the conjugate pairing, ammonium acting as an acid, forming its conjugate base, ammonia. Water we'd see is acting as a base. It formed its conjugate acid, hydronium. Very clearly this would have a Ka because it produced the acid ion. This is an acid dissociation equation. When we look at our Appendix D, we have to find the Ka for ammonium, but you will very clearly see if you spend time looking at the Kas, NH4 plus doesn't appear. However, we could find the Kb constant for ammonia, Nh3. That's the tiny table at the top of the next part there. Ammonia is listed first in the list there, just alphabetical, so it's on top. The Kb constant for ammonia I'm finding to be 1.8 times 10 to the negative 5th. No units on our equilibrium constants. How can I take the Kb and turn it into the Ka for this acid expression? Well, we know the expression Kw is equal to Ka times Kb. We have our Kb, Kw is our constant. So 1 times 10 to the negative 14th, and I'm going to just simply set up to divide by the Kb, 1.8 times 10 to the negative 5th. We're just taking Kw, dividing out Kb, and we'll have our Ka. So hit with me and see what we get. Kw divided by Kb. We get 5.5 repeating. So I'll put 5.56 times 10 to the negative 10th, the Ka for the expression in our second example. So an easy enough relationship. If I need a Ka turned into a Kb or vice versa, we'll use the ion product constant for water to do that exchange. Kw is equal to Ka times Kb. Continuing with our lesson, we'll discuss how salts act as acids and bases. This unit commonly is called the hydrolysis section. Hydrolysis, adding water. We need to examine the way that dissolved salts can affect the pH. Now let's remind ourselves of some of these chemical families we've been using in this chapter. Acids start with an H, proton donors. Bases end with an OH, they're proton acceptors. And they produce in water, after they neutralize one another, salts. These are ionic compounds. Salts are always strong electrolytes, if indeed they are soluble. Strong electrolytes always 100% dissociate. If an acid, let's just use the generic formula HX, it starts with an H, reacts with a base, let's just put metal hydroxide. Any metal, first family metal like lithium, sodium, potassium, anything like that would work for the M. Acids start with an H, bases end with an OH. During an acid-base neutralization, we make a salt, a metal positive ion hooked to a negative ion, the product here of the double displacement. And of course we would see water as the driving force. This salt, the product of an acid-base neutralization, may affect the pH of a solution. We have to discuss how we would know. Many cations, here's the cation of a base, that's the positive ion, and anions, that's the X negative, that's the negative ion of the acid, are able to react with water to regenerate either the acid proton or the base ion. And this reaction is what we call hydrolysis, simply adding water. So sometimes the positive ion from a base can react with water. Sometimes the negative ion of an acid can react with water. And if they do so, they will end up affecting the pH. Let's talk a little bit further how we might know whether or not this reaction occurs. Keep in mind X negative, what I just had on the previous screen, is considered the conjugate base of an acid. Okay, so just make that clarification. HX, whatever X might be, the last name of whatever the acid is here, when it dissociates, we get the proton and X negative. This is the conjugate base of this acid. Remember, we're leaving the water out. The conjugate pairs. For instance, chloride is the conjugate base of HCl. Acetate, C2H3O2 negative, acetate is the conjugate base of the acetic acid. These two are conjugates. We can write these words as well. Hydrochloric acid, chloride and hydrochloric acid are conjugate pairs. Acetate and acetic acid are conjugate pairs. Now here's the important note. If the conjugate base, whatever X negative is, comes from a strong acid, one of the 7 that we memorized, it will not affect the pH of the solution. No effect. However, if the conjugate base comes from a weak acid, it will abstract the proton from water and affect the pH. It will generate the base ion. Let's make sense of that and letting you digest these words. If the parent is strong, no effect. If the parent is weak, it will affect the pH. Now before we go on to the next slide, let's make sense of that because we have 2 of these examples staring at us. Remember how we said HCl indeed is a strong acid. When it's placed into water, it will 100% dissociate. into hydronium and the conjugate base chloride. The term strong means there is no little equilibrium arrow here. It would be incorrect to draw a backward arrow here. There is no equilibrium. It's 100% pushing to the right. Therefore, if there's no push back to the left, there's absolutely no way chloride has enough strength to push the reaction to affect the pH. Remember how we affect the pH? Think of Le Chatelier. If I can get this reaction to push back left, I'm going to be taking out hydronium ions, aren't I? That would definitely affect the pH. Removing acid ions makes the solution generate, a less acidic solution. So it's affecting the pH. Strong acids do not set up equilibrium. This guy has no effect on pH. But now let's consider the weak acid given in that second example, acetic acid. When it's placed into water, it does set up an equilibrium. That's the definition of weak. It also forms the hydronium ion and the conjugate base acetate. Since we set up equilibrium arrows, and again that's probably pushing more to the left than it is to the right, this conjugate base acetate will affect the pH. You can see if it's pushing left, which is absolutely an application of Le Chatelier's principle. If this is a competing reaction and I can push this reaction more left, I'm going to affect the pH by taking out some of the hydronium. The process is known as hydrolysis. Let's take a peek at what I mean. This acetate through the process called hydrolysis, reacting with water. If we consider C2H3O2 negative undergoing the process of hydrolysis, adding water, it is going to form its conjugate acid. Now remember, this right here we labeled as a base. It's the conjugate base. And here is the acid, so it's going to form hydroxide ions, the conjugate base of water. The solution has become more basic. Think of that as less acidic. Now let's stress this a couple of ways. Le Chatelier says, if I go back in this direction, remember if I can have this competing reaction, if I'm pushing this reaction left, which is exactly what an equilibrium arrow means, both reactions are occurring, but if I'm favoring this reverse order, this reverse direction, I'm removing hydronium ions. Taking out hydronium makes the solution less acidic. Showing how acetate undergoes a process called hydrolysis shows the same effect, doesn't it? When acetate reacts with water, it forms its conjugate acid and the base ion. Producing the base ion makes the solution more basic. Same thing as saying less acidic. When the conjugate base of a weak acid undergoes hydrolysis, the solution becomes more basic. When the conjugate base of a weak acid undergoes hydrolysis, the solution becomes more basic. Or tell yourself that's the same as saying it's less acidic. Remember, the parent acid must be weak for this hydrolysis to occur. If the parent is strong, there is no equilibrium, so no effect. HCl, the parent of chloride, is a strong acid, no effect on pH. The conjugate base of acetic acid, the acetate ion, will affect the pH because we have the equilibrium arrow pushing back left, making the solution less acidic or more basic through the process known as hydrolysis. Let's catch some of that up here, where it says take a look in your notepad. We did a lot of margin notes there. Let's catch up some of these fill in the blanks. Here's a conjugate base, just a generic letter for whatever that last name of an acid is. If it reacts with water, producing its conjugate, the HX, we are going to show hydroxide form. The solution will generate a base ion. So it's asking us to write this out. We might have already. The hydroxide generated, of course, raises the pH to a number that is less acidic, therefore more basic. We wrote this very equation out in our previous slide. The acetate, which is acting as a base, undergoes hydrolysis, means it's acting with water, forming the conjugate acid and the conjugate base. The solution will become more basic. Give it some thought. What effect will each of the following ions have on the pH of the solution? The nitrate ion, NO3, -1, is the polyatomic ion nitrate. And the carbonate ion, which is the polyatomic ion CO3, carries a -2. What effect will they have on the pH? Well, of course, nitrate, what is its parent acid? Add the proton back on is what I'm referring to. What is the acid that gave us this conjugate base? So if I add the proton back on, we get HNO3. This we recognize as nitric acid. It is one of the 7 strong acids that we're working to memorize. Life becomes easier when we memorize the 7 strong so that we also know the weak. It's one of the 7 strong acids. So therefore, we've learned the nitrate would have no effect on the pH. There is no hydrolysis. So since this has a 100% dissociation, HNO3 negative, when it dissociates, there is no competing arrow. There is no way the nitrate can grab the proton back and head back left. So there's no competing reaction. Nitrate will not affect the pH. The very definition of strong, 100%, points to the right. However, HCO3 -2, the carbonate, add a single proton back on and we can find its parent acid. One more hydrogen gives us the bicarbonate polyatomic ion. HCO3 negative is the parent acid. So here we have carbonate forming hydrogen carbonate. Sometimes we call that bicarbonate ion. Is that one of the 7 strong? No, it's weak. Therefore, we will see hydrolysis occur. So let's see what that means. If HCO3 -2 is in equilibrium with that salt, CO3 -2, let's show the process we call hydrolysis. If carbonate indeed extracts the proton back from water, it makes the solution more basic. Now let's show what I'm really referring to. I'm going to put an equation here. Remember this carbonate? This was the initial ionization of the parent, the weak acid. So if we consider the initial ionization of the weak acid, HCO3 negative, in water, gave us this carbonate and hydronium. This guy here is the conjugate base, and here is its parent acid. The conjugate base carbonate has the ability to push back left, doesn't it? And Le Chatelier says if this equation is pushing left, we take out hydronium. Removing hydronium makes the solution less acidic. Removing hydronium by pushing left, less acidic. Carbonate undergoes the process called hydrolysis, where the carbonate is making the solution less acidic by stealing that proton back from the water, generating its parent acid again. Isn't that what we just showed here? If I'm pushing left, I'm generating some of this parent acid, and it makes the solution more basic. So an application, trying to describe this two ways. Le Chatelier, in the first equation, shows if I'm pushing left, the solution becomes less acidic. Or by showing the process called hydrolysis, I'm making the solution more basic. And that's the same description, isn't it? We've done a great deal of talk about the negative ions of acids. Let's consider the positive ions from bases. Cations and water. Polyatomic cations whose formulas contain one or more protons can be considered the conjugate acid of a weak base. So here's our most familiar polyatomic ion. Always suspect if there's a nitrogen, we know that that is a great proton abstractor, so it's going to take the proton from the water. Ammonium undergoes hydrolysis. See that? Adding water, hydrolysis, to form its conjugate base, ammonia, and the acid ion, hydronium, H3O+. The solution becomes more acidic because we've made hydronium. Polyatomic ions undergo hydrolysis, making the solution more acidic. Metal ions can also react with water to decrease the pH if they are considered weak bases. Remember, cations from strong bases do not affect the pH. And that's a little bit of a seed here for the acid-base theory called the Lewis theory. So let's remember what the strong bases are. See that first column in our periodic table? All of those are strong bases, aren't they? They're all soluble. LiOH, sodium hydroxide, potassium hydroxide. I'm doing this from memory. We've got rubidium hydroxide, cesium hydroxide. So these are all called the alkali metals. Any first family metal whose last name is OH is a strong base. They 100% dissolve in water. Then we had some in group 2A. We said calcium hydroxide. Even though that's slightly soluble, we do consider it strong, so we can warm it up and stir it up and get it to go into water. We have strontium hydroxide and barium hydroxide. Now, these are the metals that are considered strong bases. So lithium will not affect the pH. Sodium ion, no effect on pH. Potassium, rubidium, cesium, barium, strontium, calcium, these indeed will not affect the pH. But any other metal, ion, I should add that word, any other ion, any other positive ion will affect the pH. So pick a metal, aluminum hydroxide. Now I know it's not very soluble, but if indeed it underwent hydrolysis, we're going to form some complex ions. And again, at this particular point, we don't necessarily have to understand the complex ion formation, But however, we could see that this would abstract the protons and give the solution a more acidic pH. So at this point, I'm not really comfortable sharing the Lewis theory. Let me just end it this way. This is beyond us at this point, but it's coming, a complex ion formation. I mean, it's not something that's terribly hard. It's Al, OH, take the charge and double it. So we end up with 6, and we end up with a +3 charge. So again, coming up, it's a Lewis acid-base theory. But what I want you to notice that since aluminum is not one of these metal ions that are strong, when it undergoes hydrolysis, it will go in effect to just this complex ion forms. And again, just take the subscript, which is a 3 from the original base, you double it, and you'll end up finding the charge up here. So therefore, it will affect the pH by making it, let's see like up here, it makes it more acidic. Let's keep looking at these examples. Which will affect the pH? Potassium ion, iron 2 ion, or the aluminum ion? Well, it goes by the parent, doesn't it? The parent, what is the original formula of the base? KOH, FeOH taken twice, and AlOH taken 3 times. These are what we call the parent bases. Any of those strong? Well, certainly we recognize KOH is strong, therefore no effect. But iron and aluminum both, I know they are insoluble, so they are opposite of strong, and they do affect the pH. So let's just put not strong, because I don't really want to say weak, but if forced to undergo hydrolysis, they'll form a complex ion, and those complex ions do affect pH. And simply put, if they're not strong, which these are not, if the parents are not strong, they're not necessarily weak, but they will affect pH because they're insoluble. But however, these will affect the pH, making it become more acidic. So think about that as decreasing on the number line on the pH scale, more acidic, less basic, however you want to say, but the pH is dropping as we become more and more acidic. And we're doing so by removing the hydrogen ions, or excuse me, removing the hydroxide ions, making the solution become more acidic. The combined effect of a positive cation, remember cations are positive, and the anion, which is negative in solution. And this is kind of a summary slide here. An anion that is the conjugate base of a strong acid does not affect the pH. If you remember the 7 strong acids, any of their last names would not affect the pH. Should we list those just to review? I mean, I know that we did just a moment ago, but so here's the 7 strong acids. HCl, so the conjugate base, Cl negative, no effect. HBr, so bromide, no effect. HI, conjugate base iodide, no effect. We had chlorate and perchlorate from chloric and perchloric acid, 1, 2, 3, 4, 5 of the 7 so far. We had nitrate coming from nitric acid, no effect. And of course, the polyatomic ion hydrogen sulfate, the conjugate base of sulfuric acid. So these 7 negative ions will not affect the pH of a solution, but that leaves a lot of last names, doesn't it? Any other anion will affect the pH by making it less acidic or more basic. The pH will indeed increase. It's becoming more basic. And think of that as just saying less acidic. There are 7 negative ions: chloride, bromide, iodide, chlorate, perchlorate, nitrate, and sulfate, hydrogen sulfate, whose parents are strong, no effect on the pH. Every other negative ion will affect the pH by making it rise. The pH rises as something becomes more basic. A cation, that is the conjugate acid of a weak base, will cause the pH to decrease, more acidic. So remember our previous slide. If indeed, I'm just backing up a couple slides to remind us, lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium, those metal ions, those positive ions, no effect on pH. Every other cation, a whole lot more positive ions that will affect the pH of a solution by causing it to decrease. The ammonium ion is also one to recognize. If ammonium is placed into water, you can see that it will also affect the pH. And if it puts back that proton back onto the water, you can clearly see with this example it becomes more acidic. Positive ions, we call those cations, whose parents are weak. Ammonia is a weak base. Cations from weak bases make the solution more acidic. Number 4. The cations of group 1A and 2A, we listed those a moment ago, calcium, strontium, barium, will not affect because they are strong Arrhenius bases. We listed those several times. All the other metal ions cause a solution to become more acidic, which decreases the pH. So we have repeated this lesson multiple ways. I'll give you time to make sure you're there. Number 6. When a solution contains both conjugate base of a weak acid and the conjugate acid of a weak base, the ion with the larger K constant will have the influence on the pH. If Ka is greater than Kb, the solution ends up to be acidic. If Ka is less than Kb, the solution ends up to be basic. If Ka is larger, acidic. If Kb is larger, basic. And if they are indeed equal, we have a neutral solution. Very rare, but it might happen. If Ka and Kb end up equal, knowing that Ka is another good reminder, Ka times Kb gives us Kw. So these two would indeed have to multiply exactly to be the same value, 1 times 10 to the negative 7th, and that's the Kw for water. So let's let that digest a moment and take a look at a sample problem. So let's take a peek here. Sample problem, it's asking us to list the following solutions in order of increasing pH. So I'm just making a note here. Increasing pH says most acidic to most basic. Low pH to the highest pH. We have barium acetate, ammonium chloride, methylamine bromide, which gave us the formula because that's a little organic, and potassium nitrate. So let's go to work, see what we have. Barium acetate, barium plus 2, acetate C2H3O2 negative. So we have barium acetate, BaC2H3O2 taken twice. We have ammonium chloride, just trying to get their formulas, ammonium chloride, NH4Cl. We have methylamine bromide, which is given for us, NH3, CH3, Br. And we have potassium nitrate. So 4 different salts here, potassium nitrate. These are salts, aren't they? They're not acid, they're not base. They start with a metal positive ion. They have a negative anion. Positive and negatives, we commonly call those salts. Will they indeed affect the pH? So let's consider the positive ion, and then we'll talk about the negative ion. The positive ion in the first example is barium, Ba+2. It has a parent base. The parent base is barium hydroxide. Is this a strong base? Is it a strong electrolyte? Well, we recognize that as, yeah, that is one of those listed strong one of those listed strong metal ions we had on our paper from before. So the barium is no effect. What about the acetate? The acetate is the negative ion, isn't it? C2H3O2 negative. It has a parent acid, which is HC2H3O2. This indeed is weak. So therefore, we know that weak acids do affect the pH. So this guy is a yes. It will affect the pH. How so? Well, we've learned negative ions undergo hydrolysis, making the solution more basic or less acidic. Do you need to see that just to review? Acetate will undergo hydrolysis. When it puts the proton back on to make its parent acid, you see how we generate the hydroxide ion? It's becoming more basic. So here, salt number 1 ends up to be basic. Let's talk through number 2. Ammonium chloride. The positive ion, ammonium. Its parent base is ammonia, which we know to be weak, isn't it? Therefore, yes, it is going to affect the pH. It's going to make the solution more acidic. Do you want to see, just to review why I know that? If ammonium undergoes hydrolysis, puts the proton back on the water, doesn't it? Forming its conjugate ammonia, and the acid ion, hydronium, put the proton back on the water, it's going to become more acidic. How about the negative ion, chloride, Cl negative? Well, Cl negative has a parent acid, HCl, which we recognize as strong, so therefore we know no effect. Ammonium is going to end up to be more acidic. So let's just kind of highlight how we go through. Here's first salt is ending up to be basic. Second salt we decided would end up to make a acidic solution. So far we have them being ranked as NH4 plus, more acidic, compared to the acetate, which is more basic. Well, let's keep working. We have 2 more to get through here. Methylamine bromide. The positive ion here is NH3CH3 plus, and the negative ion is bromide, Br negative. Well, right off I can know this one. I'm noticing its parent, HBr, is strong. And if the parent is strong, we know no effect. So that one I can cancel out. Here, though, this definitely is a polyatomic ion, has that nitrogen there that makes me just suspect that it is indeed going to be a salt that is, or a polyatomic ion that's going to create a more acidic solution. So here, this solution ends up to be more acidic. We'll talk about how we're going to compare those with our appendix D value. And we had one more, might as well just take a quick peek here. One more to look at, and that's potassium nitrate. Positive ion is potassium, negative ion is nitrate. Parent base, KOH, strong. Parent acid, HNO3, strong. So neither the positive or the negative are going to affect the pH. So it's not like it does not have a pH, but keep in mind it will be exactly neutral, 7.00. So this particular salt ends up to be neutral. So here's what we have so far in terms of ranking. We've got to do a little bit of detective work about these two. We have ammonium versus methylamine. So let's just kind of keep that in mind. Ammonium and the methylamine, NH3, CH3+. I'm just kind of labeling these so far as the most acidic. I have to decide which is which using appendix D. Then I'm going to place the potassium nitrate, because we said this was exactly neutral. And then I'm going to place the salt that we said was basic, and that was barium acetate. So here's what we have so far. Neutral, potassium nitrate, basic, barium acetate, and we have two salts that made this solution acidic. So pull out your appendix D and let's find some interesting facts here. And I'm going to look at, even though these are acidic, I have to find their Kb values for their parent base. What's the Kb for ammonia? First one listed there, isn't it? NH3, and that's 1.8 times 10 to the negative fifth. What's the Kb for the other ion called methylamine, but you're going to find that listed as methylamine, the parent base, CH3NH2. We just have it written in the opposite order, NH2CH3. This, by the way, is that extra proton, like NH4+. The hydrogen on the nitrogen is the proton that ionizes, so this has an extra hydrogen. So NH2NH3, NH2CH3 is the parent base. In its Kb value, 4.4 times 10 to the negative fourth. Let me make sure I found that right. CH3, NH2, the Kb value from appendix D, 4.4 times 10 to the negative fourth. But remember, these are acids, so what we have to do is flip those into a Ka and compare the magnitude. So that's simply reminding ourselves we take Kw over the Kb and we find Ka. So I won't even show that. I'm going to just flip it on my calculator. So what I'm going to do is hit 1 times 10 to the negative 14, 1e negative 14, divided by, and that first value, 1.8 e negative 5. Remember, I think we did this one earlier, 5.56 times 10 to the negative 10th. Here's the Ka for ammonium. Let me just jot that. 5.5 times 10 to the negative 10th. Let's find the Ka for methylamine using this guy. So let's hit 1e negative 14 divided by the Kb we found of 4.4 e negative 4. And we find a value here, 2.27 times 10 to the negative 11th. Here's the Ka value for this. So look at the magnitude. Now they're both extremely small numbers. These are not strong acids by any stretch, but what's the larger number? The larger the number, the stronger the acid. So if I had to rank between, remember how we had these salts ranked, this guy is most acidic. This would be in second place. Here's our third, here's our fourth place salt. We found both of these polyatomic ions turning the solution acidic. So we had to do a little math. We had to find their Ka values to decide who's stronger acid. Stronger the acid is the bigger Ka constant. So the most acidic solution, ammonium, although I didn't write their last name, I think this was ammonium chloride, NH4Cl, most acidic. Then came, so first place here, let's just write that out. So first place, most acidic. Here would be our second place. Here's our third place because it's neutral, and here's the fourth place, most basic, barium acetate. Good problem. Now I think we have one more practice in this section on hydrolysis. Let's take a peek here what's going on. In each of the following, we're going to indicate which salt will form the more acidic solution. Which salt has the more acidic solution? Now, acids come from the positive ions undergoing hydrolysis. So let's just call these examples 1, 2, 3, and 4 and talk through these. Example 1, sodium nitrate, NaNO3 versus iron 3 nitrate, iron 3 nitrate. Now right off the bat, do you notice they have the same last name, nitrate? Its parent acid, HNO3, is strong. So the nitrate will have no effect on pH. I can cancel that out. Because its parent is strong, HNO3 is one of the 7 strong acids, no effect on pH. So that leaves the only guys to consider now is sodium ion versus iron ion. So now I'm going to consider the parent base. The parent base is sodium hydroxide. It's one of those strong bases, so no effect. The pH here is exactly neutral. Both parents are strong, no effect from the salt ions, pH of 7. However, the parent base of iron, FeOH3, is not strong. For lack of a better word, we'll call it weak. So it will undergo hydrolysis, making the solution more acidic. So which one is more acidic, we're being asked? Iron nitrate. Let's take a look at the second example. Here we're working potassium bromide, KBr, versus potassium hypobromite, polyatomic ion, BRO. Let's work through here. Potassium ion has a parent base of KOH. It has the bromide ion, parent acid is HBr. Now notice from the previous example I could eliminate because they had the same last name. This case they do not. They just have the same first name. So therefore we can eliminate that. It's going to be, well, I could just say that. Here's potassium, parent base, KOH. But we have different last names now. BRO negative is different here. So here's the original ion. Here's its parent base. The original ion, parent base. We understand that they're both the same, and since they're both strong, no effect. So the potassium ion, no effect. However, let's consider bromide, HBr. Well, this is one of the 7 strong acids, so bromide, no effect. Parent here strong, parent here strong, pH comes out to be exactly neutral, 7.0. HBRO is not strong, therefore it is weak. When weak parents form, this process here produces a more basic solution. You want to see the chemistry as we're just still trying to practice. It undergoes hydrolysis to get back the conjugate acid, producing hydroxide ions. It becomes more basic, less acidic. So remember what we're being asked, to rank the more acidic. Which one is more acidic? Which one is lower on the pH scale? So if this salt makes the solution basic, and this salt keeps it neutral, KBr is lower on the pH number line than the basic salt, potassium hypobromite. This would have a pH greater than 7.00. Choosing the one lower on the number line, KBr 7.00, a neutral salt. Methylamine chloride versus barium chloride. I can see the same last names. Methylamine versus barium. Now again, use your KB chart from Appendix D. Methylamine bromide. Remember how we wrote methyl, amine. This is the positive polyatomic ion. Last name is bromide. And the other salt was barium chloride. It's chloride, not bromide. Oops. There. I just wanted to repair that because they have the same last name. So it's chloride. Alrighty, methylamine chloride versus barium chloride. Alrighty, I got up. Alrighty, so let's go to work. Here the positive methylamine has a weak parent. The parent methylamine is a weak base. Parent here is strong, HCl. Parent here, strong. And the parent here is strong. Let me just emphasize what I'm saying. We have a weak parent because the base, methylamine, use Appendix D if you're unfamiliar with that. CH3NH2 is called methylamine. Find that formula in Appendix D. Its parent is weak. The parent here is strong, HCl. Parent here is strong, barium hydroxide. And the parent here is also strong, HCl. Of course, here we would know if both our parents are strong, pH is exactly neutral. Here we have one strong, so no effect from the negative ion, but the positive ion sure will, and it makes the solution more acidic. Since we're still practicing how we know that, keep in mind the chemistry. Here's the methylamine, positive ion. It undergoes hydrolysis. It's going to put the proton back on the water, forming its conjugate base. The solution becomes more acidic. Positive ions, when they undergo hydrolysis, make the solution more acidic. So the salt with the more acidic pH is methylamine chloride. It would have a pH lower than 7, whereas barium chloride would have a pH of exactly 7. We have one more to work through in this example, number 4. Certainly pause and work ahead and just check your answers if you prefer. Here we have ammonium nitrate, NH4, NO3, versus ammonium nitrate. Oh, I read that wrong. Nitrite versus nitrate. Nitrite, NH4, NO2, and ammonium nitrate, NH4, NO3. Here's the polyatomic nitrate. Here's the polyatomic nitrite. They have the same last name, don't they? Same last name, excuse me, same first name. My mistake. We know that ammonium is a parent from a weak base. So yes, it will undergo hydrolysis, making the solution more acidic. NO2 has a parent acid, HNO2. NO3 has a parent acid, HNO3. This is strong, no effect. So the only thing happening with this salt is that it's becoming more acidic. HNO2 is not one of the 7 strong, therefore it's weak. HNO2 makes the solution more basic. So you can see these two are kind of counteracting each other, aren't they? If one's making it more acidic, one's making it more basic, whereas this guy only has the effect of the positive ion, is definitely going to be the more acidic of the 2 salts. These problems just take additional practice. Work, work, work. Find those problems, keep working them. It's the best way you can get better at chemistry is working problems. Let's finish this section up. Still more practice. Staying with me. Predict whether the salt, sodium hydrogen phosphate, sodium hydrogen phosphate, will form an acidic solution or a basic solution when dissolving in water. It is amphoteric. It can go either way, can it? Ah, good problem. First off, I noticed that sodium is going to drop out of the problem immediately. No effect on the pH. Its parent is strong, therefore no effect. So really what this problem is having us do is decide, is this polyatomic ion, HPO4 -2, going to act as an acid or going to act as a base? And what really is just coming down to finding whether or not my appendix D gives me a larger Ka value or a larger Kb value. Let's show the chemistry. If HPO4 -2 undergoes hydrolysis, and let's just call it an acid first, just to get the chemistry set up. Acids, of course, donate protons. Its conjugate base would form, and it would be PO4 -3, and it would form the hydronium ion, the conjugate acid of water. This would have a Ka expression, wouldn't it? The Ka expression, because the Ka here is producing an acid. Now, where would I find that on Appendix D? Well, I know the original acid was H3PO4. All right, so let's find that on our periodic or Appendix D. It's called phosphoric acid. It has 3 values, doesn't it? A Ka1, a Ka2, and a Ka3. What proton did we just remove? Wasn't the first one. That would be H3PO4. That would have a Ka1 value. Wasn't the second one either. H2PO4 is dihydrogen phosphate, and that's the Ka2. The hydrogen phosphate eliminated the 3rd proton. So skim all the way over. When we remove the 3rd proton from the parent acid, it's a Ka3 value of phosphoric acid, which I see on my chart as 4.2 times 10 to the -13th. That's the Ka3 from the parent acid, H3PO4. So this expression, when hydrogen phosphate ion acts as an acid, Ka3 is 4.2 times 10 to the -13th. However, it's amphoteric. So let's suppose we labeled it, instead of an acid, as a base, and it undergoes hydrolysis. Therefore, water is acting as an acid. It's accepting the proton, isn't it? A base will accept a proton. So now we have H2PO4 minus 1 and hydroxide. Here we have a base forming its conjugate acid and the acid forming its conjugate base. This indeed has a Kb expression because it's base chemistry. OH negative is forming a Kb expression. When the Ka constant we just found out up above, 4.2 times 10 to the negative 13, is flipped into a Kb, we do that by taking Ka under Kw, right? Remember that expression to put one into the other. Well, Kw is a constant, 1 times 10 to the negative 14th. The Ka, and again, remember this is the original thing, we're putting on that extra proton. So when we look at this value here, 4.2 times 10 to the negative 13, we can turn this into the Kb constant for this expression. Let's take a peek. 1e negative 14 divided by 4.2 e negative 13, and I get a Kb value 0.0238, so 024. So we're being asked which one of these is the more dominant equation. Which one will it work? Will it be an acidic solution or will it be a basic solution? And the answer just lies in the magnitude of the K constants we found. If we compare the Kb value, 0.024, with the calculated Ka value here, 4.2 times 10 to the negative 13th, clearly you see the Kb is significantly larger than the Ka value, significantly larger. Therefore, this, where hydrogen phosphate acting as a base, is the more dominant equation. It will indeed be the equilibrium expression producing the base. So ultimately we answered, will it be an acidic or a basic solution? Definitely a basic solution because our calculated Kb was much larger than the Ka. At this point, you've done a great job. You've finished with me looking at how Kas and Kbs are related, and you also practiced the hydrolysis of salts and using those values to start ranking pH of those negative and positive ions. This concludes the lesson on section 16.9. Your note pack is now filled down toward the bottom of page 13.